you.
All right. Let's go ahead and start, okay? I don't know where Sky or anybody is, so. All right, y'all. Nicely done. Cut. All right, so a couple things first while I pass out some paperwork, return paperwork. Y'all. Oh, well, last week, yeah, I'm sure you did. I'm sure I missed him.
It was thankful.
Yes, thankful.
I did like last
Yeah,
time.
yeah. Savannah, Delia, Lil,
Was that Airport
Sky.
Yeah,
No, that was 2 weeks ago, I think.
Hey,
When was this one?
I got a 10 out of 10.
Rav,
I
CM.
didn't finish my lab.
Oh, I need to turn my
Wait,
stuff. I got 100.
I couldn't finish my lab.
Okay, we'll talk about it. All right, so was this one yours?
I think that might be mine.
I think that's yours.
Yeah, that's mine.
I think I gave, this was,
Builder. Yeah, that's mine.
that was yours.
That's Bob the Builder.
Yes, I love that.
Oh,
I was pretty sure that was yours.
Bob the Builder.
Shh, guys, we gotta bring it down a notch. Y'all are super wound up today. Super excited. Here's Sky again. Delia again. Everybody's asking that this morning. Hey, what do you know? There they are. See, sometimes I just don't see it. I knew it was there somewhere. That's nice. Sky, do that one?
Which one?
Yeah, look at that. There's Sky's builder. I love the hammer. That's really good. Okay, Eleanor.
Looks like somebody's about to torture I was trying to do it.
Jackson.
I'll do it later.
Delia again. Lily again. All right, that's everything I have for you guys right now. All right, couple things. So we have normal class today. Do we have class next week?
No.
No, we do not. Why don't we have class next week?
Thanksgiving.
Thanksgiving is Thursday, so we're taking a break. Taking a break. Yes, and the day after Thanksgiving, we're going to go visit our potential puppy.
Our puppy.
Our potential puppy.
It's not potential.
We have a potential. Oh, have you not seen?
Can I see the picture?
Yes, hold on. I'll show you.
Yes.
Drew will steal it.
I've never seen a baby
No.
puppy.
Bring it down a notch.
I've never seen an image.
Delia.
This freaking thing in the entire
Drew.
Come out. I know what you're saying about. So this is him, and in this picture he is 11 days old. Because she's a hair down. Her hair down, pretty. Pretty up too. So 11 days old here. So we're going to go meet him the day after Thanksgiving. Now, if we decide we're getting him, then he will come here the first weekend of January, so he'll be back after Christmas in here. Okay, so that's what we're saying. So there's no class next week, right? Because it's Thanksgiving.
Listen.
No, but we're taking it off.
Yeah, hold on. There's one in here. Okay, so then we're, listen, y'all are super chatty. You need to listen, okay? Then we have class on the 3rd, right? Class on the 10th, normal classes. Then the 17th is our Christmas party and movie.
Are we doing?
And the midterms. That's all that day.
Are we doing the class on February 11th?
February 11th. What's February 11th?
My birthday.
Oh, yeah, we don't take off for your birthday, but you can bring food.
We won't stop working, but you can do more working.
Yeah.
Well, yours is colored. I would say y'all are tied because hers is more detailed, but yours is colored. So I'll give her a thingy and I'll give you a thingy too. Because nobody else covered it, right?
No.
All right.
I was busy.
So that's step 1 is remember our schedule. You have extra time. We are going to grade our homework in here today, so I don't have that waiting for you over break. All right. And if we can get through lab today fairly quickly, it would be awesome if y'all could all sit down and try and crank it out. I'm really not sure quite how long it's going to take.
I'm trying to finish my lab all
Says
in
usually-
today.
Yeah, you can always try and get them done in class. That's always a good thing to try. But if it doesn't get done in class, it's not the end of the world. You just have to
Send the world to me.
take it home and do, and then look up, what you need to look up to get help on your on the forum. Remember, help is almost always going to be on that forum.
So
Here it
what days
is.
are we gonna be here? 'Cause
You're not here next week. And then we're here until it's time for a Christmas break. Our last day is the 17th. It's all in your, you have it all in your syllabus. Everything is air. So this lab says time 45 minutes, so we should have time. If you guys are efficient today, we should have time to knock out
Are
lab.
these the only
Get it written
2
down.
pages for lab?
Yeah, it's only, let me see,
There's only 2 pages.
1, yes, 2. That's it.
It's way too
Right.
late.
All right.
Same.
Hmm?
There's no gummy bears working style.
Work
Did
as
you know
styluses. Let's not do that.
When
That's
you
gross.
eat a gummy bear, you're eating pig.
Yeah, gelatin or horse. They do. Sometimes it's used to be horses' hooves and stuff, but now mostly it's they get the gelatin from collagen, and that comes out of bones and ligaments.
Yeah.
All right,
I'll
so
have
let's
it.
go
I'll
ahead
take it.
and
I'll
that's
have
what Jello too, though.
I want it, but I don't want it.
All right, I'm gonna share my screen now. We're gonna move on to our notes.
Imagine if you forgot to record
Yeah,
again.
oh wait. No, it's recording. I don't know why it was weird. The one time it forgot, and the other time it just didn't.
And the one time I forgot, I went when she told me to raise, say hello or something.
Okay,
I
So-
learned a new sign.
our lab today is going to be on pulleys, and you had a lot of simple machines in your notes, didn't you? A lot of simple machines this week. All right, so we're going to talk about mechanical advantage and efficiency. And I also got you guys some various screws and screwdrivers. So you can, well, no, because they're Jason's, but you can, there are some bolts in here and nuts. Yeah, there are things like nuts and bolts. Huh?
Eatable nuts?
No, not edible nuts.
I thought
Nuts
it
that
said
go
edible
on like this, right? And just basically because you've probably seen all these things before, but you've
No.
probably not really thought, like really thought about them. So I got these out just so you guys can play and then really think like look at this. What would this be good for versus, and this is flat
Try
on
to
the
make a
bottom.
playground.
Let me
Making it so
show
easy
you.
to extend without cutting out
Like
areas.
think about it. Don't answer right now. Think about it. There's this screw there's a screw right here with a pointy end. No, don't think it, just think about it. And then there's a bolt right here. And look at the differences between them. They're about the same diameter.
I feel like I should know this because
So I
my
just
grandpa
don't, not
has
now. We're
shown-
gonna
Okay,
go,
screws?
Drew,
Can't see it.
one's a screw, one's a bolt. We're gonna come back to
What's
it.
the difference?
Well, we're gonna talk about it when we get to the part about screws in a few minutes, but I just want you to see them and think about it for a minute, all right? So does everybody have your notes out? Ooh, what you need? Oh, you do? Okay,
I
we'll
have
get
my
there in a
weekly
minute.
notes.
You have what?
And my weekly notes.
Yeah, look for your notes, not just your questions, but your notes, okay?
Was I supposed to turn the notes in?
No, don't turn them in.
No, these.
Nope, we're gonna grade them today. That's why I put the little sign over there. All right, so a machine,
Second.
it's okay, you can look while we go through it.
These
A
are-
machine is a, yep, no, that's last week.
Come on.
So a machine is a device that can help you do what?
Work.
Work, very good. In a way that's easier or more effective. So a machine makes work easier by changing the amount of force you exert, the distance over which you exert the force, or the direction in which you exert the force. So those are the three things that machines will do.
How many
Change
pages?
let me see.
2, I think.
Yeah, it wasn't too many, I don't think, yeah. All right. So machines will change the amount of force you exert, the distance over which you exert it, and the direction.
I found a bounty plan.
Did you? Where is it?
I don't know if it was already found. I don't even know.
Oh, the last one.
Oh, did we get to it yet? Okay, tell me when we get to it, and I'll.
Did you say
No,
no,
it's
the last?
It's on the last one on this page. Okay.
I said bounty point, and I'm like.
So anybody want to read the next paragraph there?
bounty? Will we get
What's the
money
next?
for it?
The next paragraph. Anybody want to read that?
Where is it?
The paragraph next to the triangle. Go, Delia.
The force you exert on a machine is the input or effort force. The force exerted by the machine is called the output force. To calculate the amount of work a machine does, multiply the force times the distance.
Awesome. So this is another one of those triangle deals. Remember we had one last week, or was it week before? You guys?
It was 2 weeks ago.
2 weeks ago with you guys. All right. So remember, they're super easy. If you can just remember what's in the triangle, you can remember everything else. So what goes at the top?
W.
W. What's that for?
Work.
Work. Okay. And what goes right on? Wait a minute. I drew it upside down. Okay. I only had 2 cups of coffee. You'd think I'd be with it today. Ay, ay, ay. I know better than this. Jeez, y'all. Okay. There's your work.
Pyramid.
What goes here? An F for force.
You need a dot. You
Hang
need
on a second. We're coming back to it.
Oh.
What goes here?
Felicia will
D.
done.
Felicia.
Yeah, the D, the distance. All right.
Wait,
So you guys had the did you have this last week or was it the week before last, right?
I remember that. I kept the word Felicia in my head.
Last week we did Felicia will done.
That's right. Okay. So there it is.
Felicia will done.
And so what went here? Do you remember?
Times.
Times, and these were
Divided.
divided and divided. So if I want to find work, what do I do?
Force times distance.
Force times distance. And why is the D not D? Why is it not that?
That's
something else.
What did that stand for?
Density.
Density. Right. We gotta get that right.
Density.
Right. I knew density. If I want to find force, what do I do?
You have to,
Work
you have to
times
hit
the-
something.
Work time.
I don't know.
Work divided by distance. And if I want to find distance, what do I do?
You have to find a track.
True. Answer the question seriously.
Work divided.
Work divided by force. Okay, that's right. Good. You guys got it. Those are, if you can remember these little things, they're super duper helpful. So I'm gonna have these will probably be on midterm, something similar to that, to help you remember what your formulas are. Yes.
I have a question. Is it cheating if your parents help you a little bit with the test?
Well, what they do with your test is up to you because they're your teachers technically. I'm facilitating your science class, but as a homeschooler, your parents are the only person who can technically teach.
And your parents read it to you.
Yeah. It's whatever your parents want to do with your tests are entirely up to them, and I explain that to them. I just report the grades as they are and move on. Some of them want their kids to study from a study guide. Some of them like from their notes. Some of them want them to study the book.
I studied
Yeah.
from my notes.
Yep. It's always, if it's on the test, it's going to be in the notes every time.
Last week I
Yes.
accidentally read the whole chapter of 12.
Ah,
Is it?
that's right. What you got?
Is it okay if I stay a little bit after class with my sisters have a dentist?
Sure.
And also, where do I turn in my lap?
Well, you can put that up there when we're done. Don't worry about it. All right. So sometimes
Stay with Drew.
Sometimes it is advantageous for a machine to multiply the distance over which a force is exerted, while other times it's advantageous for a machine to change the direction of the force, right? Okay, so think about a situation where it might be advantageous to multiply the distance over which a force is exerted. We are under the triangle where it says sometimes it's advantageous for a machine to multiply distance. So what's an example of that? Can anybody think of an example of that?
A conveyor belt system.
Maybe.
A bicycle?
Think about a very,
Or is that the lever
think about the
thing?
most, yeah, the lever thing. Think about the most simple machine you can think of. Okay, if I
Right.
wanted to, all right, hold on. Say I want to pretend this is not a screw top. Ooh, it's really dusty, but anyway, pretend it's not, ugh, that's the garage for you. Pretend it's not a screw top. Pretend this is a paint can.
Okay.
Which one of these is going to be easier to use? This one to open the paint can
I can't see.
or this
That
one?
That one.
Right, because we've multiplied our distance over which our force is
It's also a
I was
flat.
gonna
exerted.
say something funny.
It's also
like
bigger, yeah.
Call a professional to open it.
And then for direction, so direction, let's say it's your job to get a flag to the top of a flagpole. Is it going to be easier for you to climb up the flagpole and hoist the flag up, or stand at the bottom and use what?
A pole.
A pulley and do this?
Pulley.
Yeah, okay, so that's when we're distance.
Nobody wants to climb.
Yep.
Especially
Beside my
the
breath.
bowling.
Mhm.
Nobody wants to climb beside my
So a machine's mechanical advantage is the number of times a force is exerted on a machine. It's multiplied by the machine. So the number of times a force exerted on a machine is multiplied by the machine. So whatever you put into the machine, it gets multiplied. That force comes out the other end, and that force, however many times it's multiplied, is your mechanical advantage. So you've got mechanical advantage is a ratio of output force to input force. So think about this for a minute. What's a ratio mean? Does anybody know? Can anybody describe it? Ratio is a fraction. Very good. So what?
Does that mean if you're going to have, let's say, like a 100-pound weight on the ground and tie it to a rope and you put it on a pulley, if someone's going to lift it, it would be like 50 pounds?
It depends on how many segments of rope you're using.
One.
That's how it works. Do you remember when we were at the Nemo Museum in Amsterdam and there were the chairs with the pulleys?
Yeah.
Okay, so there was a chair and you sat in the chair and there was one pulley above your head and you were supposed to hoist
They
yourself.
had that at the Children's Museum.
Then there were two. Yeah, this was the Children's Museum we did in Amsterdam. There were two, then there were three, and it got easier and easier.
Is that in Boston?
There are lots of different ones. We saw it in Amsterdam.
I think I saw that in Boston.
So a ratio. So let's talk about ratio. So Jackson is right. A ratio is like a fraction. So let's say that I told you for every 10 bucks,
Ooh.
there are
Money
30 does.
Isn't it doves?
No,
Oh.
bucks and does. Okay, you know, deer,
Yeah.
female deer, doe deer, female deer, and a buck with antlers. Okay, so what? Finish. Wait.
Do you know why people call bucks, dollar bills, bucks?
Yeah.
Because the Indians used the skin of the bucks as basically money.
Yeah. Mhm.
I learned it as like they used to sell like
Heard
one
lots of different
deer.
ones. Yeah.
One deer was $1.
Oh gosh. Hang on, let's get back to ratio. Then we'll tell other stuff. So, you know, the way you would describe this is you could say there are 10 bucks to every 30 does. So the ratio is 10 to 30. But these are nice even numbers. So you could actually take these away and say your ratio is 1 to 3. For every 1 buck, there's 3 does. Now, I don't know if the ratio is actually 1 to 3, but typically there are more females in a population than males. Can you think about why?
Because females are awesome.
Well, there's that. Why would it be more advantageous
I thought there
is
were
as
more
a
males.
population to have more females than males?
I thought there were more
Because
males.
I'm assuming the
females
bucks
give
get
birth to
hunted
more.
more than the does.
So it has to do with reproduction.
Oh, I know.
What?
Probably because the bucks have to do the dangerous stuff and go out and hunt.
No, deer don't hunt.
And they get hunted.
They're herbivores. Okay, this is
No,
it.
they have to protect the
Say
bucks,
here,
have to
do you
protect
know?
the family.
Why?
Yeah.
It's easier to have a girl than a boy if you're a deer.
Maybe. Okay, so here's why. How many,
Bambi.
Wait a minute, wait a minute.
Because they wanted to grow
how many
up.
offspring, babies, can a female doe produce in one season? A female deer or doe? 1 or 2 usually. Sometimes they have twins, but it's 1 or 2
I was really off.
per pregnancy.
Oh, because males
How
are more
many-
special.
How many offspring can a buck produce in the one season?
0.
However many does he gets pregnant. So when you think about this, you get more females than males because you don't need as many males to increase your population. You need more females because the males can go around and spread their DNA all over, which they do every spring, and the females don't get but so many opportunities, right? So typically, especially herd animals, there tend to be a higher ratio of females to males. So we have this 1 to 3, all right, with our bucks and does. So what if so you could say that the entire population is 4, and out of the 4, 1 of them would be a buck, 3 of them would be a doe, which would give you 4 over 4, which gives you like the 1 unit of population you're talking about. But basically you have 1 to 3 when you're talking about this ratio. So it says here, mechanical advantage is a ratio of, let's say, ratio of output force to input force. So you have output force to input force. And together you get the whole thing. So for a machine that multiplies force, the mechanical advantage is greater than 1. The output force is greater than the input force. So the output force is greater than the input force. So think about this. This is where you need to have a math brain for a second. If the output force is going to be greater than the input force,
Then the alligator
Then-
will eat the greater thing.
for it to be greater than 1, let's use our numbers again. Let's use different numbers. Let's not use our 1, 2, 3. Oh, hold on.
I'm also.
So if your machine, listen, if you talk, you won't understand. So a machine that multiplies force, right? You're making the force bigger, so your output force is going to be greater than your input force. So if your output force to be greater than your input force, your mechanical advantage is going to be greater than 1. And here's how. So let's just say our output force is just 1 bigger than our input force. Let's just use random number, 4 and 3. If we put this as a fraction where you do output force to input force, That's going to be 4 over 3. Is that greater than 1?
Yeah.
Yeah, because it's 1 1/3, right? It's greater than 1 because the bigger number is on top. Is everybody following me there? Okay. So we're going to say for a machine that multiplies force, okay, you're going to have your output force over your input force, and it's going to be greater than 1. Right? Now, what does it say for the next one? For a machine that multiplies distance, the mechanical advantage is less than 1 because the output force is less than the input force. So, if we have our, now we're on distance, all right? You with me so far?
No.
Yes.
Yep.
Our output force over our input force, right? What's it say? It says the output force is less than the input force. So let's just use our 3 and 4 again. Okay? Is this greater than 1?
No.
No, it's not. So if the machine multiplies distance, the output force over the input force is going to be less than 1. Right? That's less than 1. 3/4 is not a whole number, right? You know how fractions work? 3/4 is not a whole, right?
It's
Everybody-
75
everybody
cents
follow
out
me?
of 100.
We do 4. This is 3/4 of the pizza. It's not a whole pizza because we still have a piece out, right?
I want a pizza.
I want a pizza
I
too.
want pizza.
Pizza's disgusting.
All right, so this last one then.
Wait, what? I want a lava cake.
So if a machine, Drew, focus. If a machine changes, what's change? Remember this?
Did you hear what she said?
I did, yeah, delta. So let's say it changes the direction, okay? The machine changes the direction of a force. Here we have our output force over our input force. What does it say here? If a machine changes the direction of a force, the mechanical advantage is what?
Right.
Is 1. And it's 1 because they're going to be the same. So this would mean like our output force is 3 and our input force is 3, so it's going to equal 1. Now remember we said the mechanical advantage is the number of times a force exerted on a machine is multiplied by the machine. Right? So if you put in a force 1 times a force, any number, x times, that's going to be weird, I shouldn't use x. Let's say y, because of the times signal. Y can be any random number times 1 is going to equal what? What's any number times 1?
That number.
The number itself,
Right.
right? Good. So that, are y'all following me or are you a little lost?
I got it.
If you're lost, say you're lost. Are you lost?
Absolutely.
No? Yes, ma'am.
Pocahontas didn't save Captain Smith.
Okay. There you go.
So I have a riddle.
That's your random fact for today. Thank you, Eleanor. All right, so the efficiency of a machine is the comparison of the machine's output to its input, and it's expressed as a percent. All right, so what's a percent mean?
It means
50%
1 out of 100.
Right. So yeah, the
1 out of
word
100.
percent. All right, you got, here we go back to roots. Remember we talked about Latin and Greek roots
Think
in
about
science?
dollars.
Shh, hang on. So you have per cent. If I said these apples cost $1 per apple, what other word could I use in place of per?
And
That, yeah,
$1
sort of.
an apple.
Yeah, you could say it's like $1 for an apple, $1 each apple, right? What per means in this case is like out of or a part of. So it's what part of, and then what does cent mean? We did centimeter.
1 out of 100.
Out of 100.
It's 100. Yeah, cent means 100. Because remember, a centimeter, how many centimeters are in a meter?
100.
There you go. Okay. So
How many
This means-
hectoliters are in a meter?
part out of 100. So if you had something that was 3 out of 100, if you think about this as pennies, and you have 3 pennies out of 100, okay? What you actually have is 3%. That's a terrible 3% of your dollar or 3% of whatever. All right. Same thing with, and maybe you have 50 out of 100, and that's going to be 50%. And you know that 50% is about a half, right? If you have 50 cents, if you have 2 quarters, you have half a dollar, right? Okay. So the efficiency of a machine is the comparison of its output to its input. Well, comparison That's a ratio. That's what we just did. So it's the comparison of its output force to its input force. It's the same thing that we just did, but what's the difference? It's expressed as a percent. So to express it as a percent, it says in the next line, to calculate the efficiency of a machine, divide output by input. That should say work, shouldn't it? That's the walk you guys caught, huh? Yep, waka waka. There used to be a show on TV when I was a kid. It was one of those cooking shows, and it was a guy who cooked Chinese food. He was a Chinese guy who cooked traditional Chinese food, and his name was Yan, and the show was called Yan Can Cook. And at every commercial break, he'd say, "Be right back, don't walk away." It was so funny. I loved him. He was great. Don't walk away.
Don't
Doesn't walk
away.
He made a pun. So, all right. If the efficiency of a machine is output, right, which we just did, divided by input, but it's expressed as a percent, then all you have to do is times 100. So, say you have, now this is where it gets tricky, and this is where decimals and percents come in. Who has done decimals and percents in math? Anybody done them, like really done? You did a whole year of them last year. Okay, good. So let's say our output force equals 3, and our input force equals 4.
Okay.
All right? So we're gonna take 3 divided by 4. Does everybody see how we got that?
Yes.
Okay, times 100. Now there's a bunch of ways you can go about doing this. Lots of ways you can go about doing it. You can do 300 divided by 400, and then you just gonna knock these off. That seems like a lot of extra work.
Oh.
You can do 3 divided by 4. All right, so it's gonna be less than 1, right? Because you got a smaller number on top. 4 didn't go into 3. Nope. So then you gotta do a 0, and then what do you have to do? What do you do in this case? You gotta add a little decimal, right? Well, let me ask you this way. Let's think about 4. I bet you know this one. What number goes into 4 evenly?
2.
Sorry. What times 4 is 100? That's what I meant to say. What times 4 is 100? What coin do you have 4 of to get a dollar?
Oh, a quarter.
Quarter's worth how many cents?
25.
25. All right. So let's think of this one this way. Because when you get into these, it's time to break out your calculator in lab. You don't have to if you like to do that, but a lot of people be like, nah,
Yeah.
and that's fine with me. So if you know that 3/4 is 100, what's 4/4 is 100? What's 3/4?
What was it?
What's 3/4?
75.
So 75. So basically, if we take 3/4 and let's just use our little quarter times 25 times 25. What are we gonna get here? We're gonna get 75 over 100, right? 75 over 100. And as a percent, if you multiply this fraction times 100, that's 100 over 1, right? These go away, and you get 75 over, and you end up with 75.75 if you're doing it as a decimal. If you're writing it as a percent, which is what we're doing here, you get 75 and 75. So you get 75%. So 3/4 is 75% of something. I mean, think about it, you know that, right? All right, so that's efficiency. So that machine that would be 75%, it would be a machine that multiplies distance. Do you see? Because it says the mechanical advantage is less than 1. Because the force is less than 1, and our mechanical advantage was less than 1 if it's 3/4. Yeah, it gets a little crazy. All right. So this next page. So we have efficiency, work output over work input equal times 100. So really it's not input force, it's work input output. Anyway, same numbers. A machine's actual mechanical advantage is the ratio of output force to input force, and it represents the advantage the machine provides in a real situation. The mechanical advantage of a machine without friction is called what? What do we call it without friction?
Without friction.
Yeah.
Yeah.
Wait, she's got it. Go, Delia.
Ideal mechanical advantage.
Ideal mechanical advantage. So there is never a machine that will ever produce its ideal mechanical advantage because, Drew, don't do that, you break your binder. Because friction is always present. Now in a vacuum and stuff, you got it so little that you probably get really close. But here in the real world where we live and put machines to work, you'll never ever get a machine that meets its ideal mechanical advantage because there's always friction. So think about this. Say you have a piston, right? So a piston is like a cylinder that moves inside of a pipe. And a lot of, they have them in car engines. They have them in train. Think about a train wheel. You know, on the train wheels, there's that big piston that moves back and forth and pushes the wheel forward. All right, what do they put in there to help it move more smoothly? No, what do they put in the cylinder?
Oil.
Yeah, oil or grease. Okay, they've lubricated it so that it moves. It doesn't. Imagine if you didn't, it would be really hard. There'd be a ton of friction. But still, let me ask you, if that train piston had moved and moved and moved for 100 miles, would you want to walk over when the train stopped and put your hand on it?
No.
No, why not? Why not,
It'd be
Savannah?
hot.
It'd be hot because what?
Because of the friction.
Yeah, I mean, right?
I've been moving.
If you put cooking grease on your hands and did this, it would be easier and there'd be less friction, but it doesn't go away. So nothing's ever going to reach its ideal. Yes.
Even if there's like hoverboards 100 years from now,
Mm-hmm.
there'll still be friction because they're hovering, but they're
Yes.
still cutting through the air.
There's always fluid friction,
Can I
air
say
and water.
something?
What?
I gotta say something. I was very, very crushed when Marty McFly lied to us and said that there'd be hoverboards. And
He did say, yeah, that's not true.
How dare he?
It's making it Back to the Future
Actually,
reference.
technically, there were hoverboards like wheels on wheels in
Yeah.
like 2016.
True.
You're off.
All right, let's get back on topic. All right, so actual mechanical advantage is the output force over the input force. And ideal mechanical advantage would be input distance divided by output distance, but we're never going to get there, right? It's just never, ever going to happen. So let's look at our simple machine types because we got about 10 minutes before we need to go to lab. So there are 6 types of simple machines. Somebody tell me about the first one. Who wants to do the first one? Jackson, it's yours.
Inclined plane.
Okay, what's an inclined plane?
It is a flat surface along which a force moves an object to a different elevation.
Yep, keep going.
And the inclined force efficiency is impacted by friction.
Yep, absolutely. Okay, so if you look at the little picture, hang on, Drew. If you look at the picture, they've got an inclined plane going down, one going up. So they got the wheelchair ramp. The stairs are a type of inclined plane, right? It's
Why?
just levels up. Now look at the guy pushing the hand truck with the boxes. What's he doing to reduce his friction?
He's
You know what he's doing?
using rubber wheels.
He's trying to get, he's using wheels. He's trying to get those boxes up that ramp. If he stacked those 3 copy paper boxes, especially if they're full of copy paper, and tried to push them up the ramp, how well would he do?
The boxes would probably fall and crash on him and he'd die.
Well, they would be very hard, that's for sure. But he put them on wheels, and that's going to reduce his friction. So you can determine the ideal mechanical advantage of an inclined plane by dividing the length of the plane by its height. Now, if you look at the guy with the wheelchair right there, that's kind of a steep ramp, I think, for a guy in a wheelchair. There are rules about, no,
Where's the wheel?
it's in the top
Where's the-
left of the picture with inclined planes. Drew, stop talking out of turn, please. Thank you. You didn't, did you? No, we'll need to do that in a minute. So you can, if you were to build a public building and you have to have a wheelchair ramp, right? Our law says you have to have a wheelchair ramp to make it accessible. There are rules. Oh yeah, there's a rule about the grading. It can't be too steep because if it's too steep, it could be really dangerous. Somebody could tip, and that would be really bad. So there are rules about the absolute steepest it can be. This one looks like a private house, so I'm thinking he can get away with sticking one on his house that's a little steeper than maybe it should be. So to find your ideal mechanical advantage is the length of the inclined plane divided by the height of the inclined plane. So somebody want to tell me about the next one? What's the next one? Go ahead, Jack.
A wedge.
Okay, a wedge. What's a wedge?
A wedge is a device that sticks at one end and tapers to an edge at the other end.
Mm-hmm.
It is a V-shaped object whose sides are actually 2 inclined planes sloped towards each other. A thin wedge of a given length has a greater ideal mechanical advantage than a thick wedge of the same length and it more effective.
Okay,
That's
good.
it.
So wedges.
Oh, it more
When you
efficient.
get to when you think about this, which we're going to in just a second, what's at the very end of it? Oh, what do you know? That's a wedge, isn't it? It's a pointy wedge. Huh? What?
Is this supposed to be it or its? And
It or its?
And it more efficient.
Is, there you
Yeah, I
go.
noticed
It's
that
two. You found them.
I
It
noticed
is.
that one.
All right. So look at the options here. Look at the options there for types of wedges. Now you probably don't think about it very often, but that zipper, if you look at a zipper, it's full of little tiny teeth that hook together.
Yeah.
And the actual zipper itself, the pole, has a series of wedges in it at different angles that push those teeth together. You can't push them together with your fingers. It's really difficult. I've tried. When they get broken, I've tried to do it. You can pull them apart because you can get a lot greater force ripping, but pushing them together is really, really difficult. But the little wedges make it super easy, right?
In pre-K, I always had to ask. In fact, I always had to
Get
have
help. Yeah. All right, so let's look at screws, and then I'm gonna give you these for a minute. What's a screw? Who wants to tell me what a screw is? Go ahead, Delia.
It's like that you use a screwdriver to
Mm-hmm.
like to screw into something.
Yep. What do your notes say to describe it?
A screw can be thought of as an inclined plane wrapped around a cylinder. Screws with threads are closer together, have a greater ideal mechanical advantage, and they are more efficient.
Very good. Okay, so a screw and a wedge are both technically inclined planes. They're just different types of inclined planes. So while there are 6 types of simple machines, some people will group wedges and screws as inclined planes. So then your number is no longer 6, right? You're down to 4. And that's perfectly fine. What you have to understand is that they are both types of inclined planes, because if you have a wedge, right? So if we look at, where to go? Here's one. There is a wedge at the end of a flathead screwdriver, right? This side's an inclined plane, this side's an inclined plane. It's just 2 inclined planes slapped together. When you think about it, it's not really something different. And this is an easy one to see. This is an inclined plane wrapped around a cylinder. Here's your plane, and it's wrapped around. Really obvious in a parking garage, if you've ever done one of those in the car, where you think you're gonna puke because you've been in there forever and you just keep going around and around. That's exactly the same thing. That's how you're getting to the top. You're just winding, yeah, up and up, or a spiral staircase. If a staircase is an inclined plane, then what's a spiral staircase?
Wait,
An inclined
like
plane,
the coin-
right?
That's
It's
like the coin thingy where it looks
coin
like it's
thingy.
going into a black hole.
yeah,
Put
spin
it
around.
in.
Yeah, okay, yeah, That's a funnel. So that's basically like wedges.
Yeah.
Yes.
I have one. Have you ever been like on a mountain and you keep on going around it?
Yes.
I've actually gotten car sick.
Oh yeah, I get car sick by just like sitting in the car. So I'm with you.
Ever.
So
Okay.
when we talked about thinking about these for a minute, we have just a couple minutes left, but does anybody want to give me an idea about these? Which one do you think would be easier to turn with the screwdriver? The one in my left or the one in my right? Raise your hand if you vote for left. Very good. And how about right? Okay, so which one do you think is less likely to come out of whatever it's screwed into? The one on my left or the one on my right?
Left.
Who votes for left? And who votes for right? Okay, so here's the differences. So they're about the same length. They're about the same diameter. The difference is this, do you know what kind of screw this one is? Do you know what it's used for? It's a wood screw, very good, because it has a point. And it's got big, yeah, see how thick, how deep the threads are on this. They're spread apart, but they're deep. Do you know what this one is? Flattened. It's a bolt, or it can be called really a machine screw, because it's actually, it doesn't have a bolt head, it has a screw head. So technically it's a machine screw. These go into, where'd my nut go? These go into nuts. And that's, here's one. And this is why they're different. So I would not take this guy and put it in my car and like screw it through a hole and expect it to stay there. But this guy screwed in through a hole that is exactly the diameter of the cylinder, not screw, but cylinder. Look at that, I can screw it through my fingernails. That's kind of fun. Because see how many times it has to rotate before it comes out? Like a lot, right? All right, so stop being gross. So anyway, these go, you put a bolt on the other end, sometimes you put a washer, all that good stuff. So somebody tell me what a lever is, because we only got a couple minutes left and I want to check your homework. Go ahead.
A lever is a rigid bar that is free to pivot or rotate about a fixed point. The fixed point about which a bar pivots or rotates is called the fulcrum.
Very good, Eleanor. Okay, so we did levers last week in lab, so you guys should be pretty familiar. You got first class levers where your fulcrum is between your input and output, right? You have second class levers where your output, whatever you're lifting, or sometimes it's called your load, right, is located between the input and then the fulcrum, like a wheelbarrow, right?
Yeah, like this.
And then you have a third class lever, which is when your input force is between your fulcrum and your output. And the pictures at the bottom and the pictures on the left, pictures on the bottom and the left are pretty helpful in showing you examples, all right? So it also says you can calculate the ideal mechanical advantage of a lever by using there's another one, the distances. Wow, y'all caught 3, huh? Did anybody catch that?
Oh yeah, he distance.
Yeah, oh, I caught that one, huh? Okay, 2.
No, I did. But
You did,
I
okay. The distance is between the forces and the fulcrum. All right. Anybody want to tell me about our last one? Oh, no, second to last one, wheel and axle. Anybody want to read wheel and axle? Savannah.
Wheel and axle consists of 2 circular or
Cylindrical, that's a tough one. Yep.
objects
Yeah.
that are fastened together and rotate about a common axle.
Right.
get some water?
Yeah, we'll be done in like 3 minutes if you want to just hold on and then grab it. So you can calculate the ideal mechanical advantage of a wheel and axle using the radius of the wheel and the radius of the axle. Divide the radius where the input force is exerted by the radius where the output force. So that's radius of a wheel divided by radius of the axle. Okay, these are wheel and axle. Here's your axle. Here's your wheel, right? And sometimes your axle turns your wheel. Like if you think about your axle turns your wheel, well,
Maybe a car.
cars are kind of more like yeah, but it's hard to see is what I'm saying, because most people don't like get up under their car. Okay, but a Lego car, you put the axle in the wheel and then you push, right? So the force in that case is
wheel
coming
here-
from you.
The
Sometimes they
wheel
move
moves, but the
together.
axle doesn't.
Sometimes they move independently,
Oh,
right?
Oh,
Yes.
one of those hot dog things that rolls.
Yeah, that's a good one, the hot dog things that roll
I'm
around.
hungry.
So hang on, Eleanor. So there's
I
some
don't like hot
examples:
dogs either.
screwdrivers, windmills,
Okay.
cars, bicycles, rolling pins, fans. All right, let's talk about pulleys real quick, and then we're going to go over our homework answers, because we're going to do pulleys in lab today. So I'm going to go over them quick because you'll get a lot of work on them in lab today. So pulley is a grooved wheel with a rope or chain wrapped around it. Technically speaking, it doesn't even have to be a grooved wheel. If you threw a rope up over a branch and then used it to lift a log, that's still a pulley. If anybody's ever done that, okay, that's still a pulley. So you have fixed pulleys. See that one in the picture there? A fixed pulley only changes the direction of the input force. You pull down, the load goes up. See like that picture? Movable pulley can change direction and size of the input force. So the pulley's now hanging, it's fixed, the rope is fixed above, and the pulley's hanging, and you can raise up and down, which will raise and lower the pulley and the load, okay? And you see those sometimes on, who watches football games and sees the camera? Do you know the camera? Well, it's not even now it may be a drone, but for a while it was cables that stretched across the field, and then the little camera would zip all over. That's how it's working.
It's a mix between a drone.
Okay, so then you have compound pulleys.
Are you American?
Yeah, exactly.
So annoying.
So you have compound pulley,
I know.
and then and then a block and tackle. Okay, the compound pulley, a block and tackle is a type of compound pulley. But if you look at them, you can see how they're different. In the one that's labeled as compound in your notes, you've got the rope fixed to the top, and then the load and the pulley are hanging, and the rope goes through another pulley that's fixed. So then you have a block and tackle, and a block and tackle, you're raising and lowering the load with a pulley at the bottom. My grandfather had a grandfather clock. And if you've ever wound a grandfather clock, it's a block and tackle. But there's a little pulley at the bottom, and then the weight, and then the cable goes up into the top, and you turn a key, and you can watch the cable go like this. And as it does that, the weight comes up, and the weight is what it uses to keep the gears moving. Question?
Is this basically the same as whenever you go rock climbing? The weight is basically you, and then this is the person that's belaying you. They pull
Yeah.
down on it and you go up.
Yeah, that's exactly how it works. Absolutely. Once they have that little what is it called in the top? The anchor. There's a word. Whatever the anchor is that the rope goes through at the top. Forget there's a word for it. But yeah, that would be your pulley essentially. Most of them actually have a tiny pulley in them, a little tiny pulley on a hook. All right. So lastly, compound machines are made of a combination of 2 or more machines. An example of a compound machine is gears. Bless you. In which one wheel and axle is linked to another wheel and axle. Technically speaking, this is a compound machine because this is your wheel and axle, and look at the end, we have a wedge, scissors, staple pullers, all these things are, gears don't have to be in a compound machine. What you are creating in your final lab of the year, your final project, your big team project, the Rube Goldberg machine is nothing but a string of simple machines forming one massive compound machine. Massive, to do one simple job. And you're going to watch your energy transfer from machine to machine to machine. It'll be fun.
What time are we supposed to be doing that?
Right now. So we're going to go over our answers real quick.
Okay.
All right, so lesson 15, let's look over our homework real fast because we got to start lab. You test a machine and find that it exerts a force of 5 newtons for each 1 newton of force you exert operating the machine. What is the actual mechanical advantage of the machine? Jackson? 5, correct. So you got output force divided by input force. So your AMA is 5 newton over 1 newton or 5. Everybody understand that?
Yep.
Okay. Number 2, explain how machines, are you looking at your work, Drew? You got to look at today's lesson 15. No, you shouldn't have. There wasn't anywhere to hand it. Explain how machines can make work easier, even if they don't decrease the amount of work you do. Delia?
Because machines make work easier by increasing input force or increasing distance.
Perfect. Perfect. All right. Number 3, give an example of each of the types. Go for it, Lily. Let's hear yours.
A screw, a jar lid, a wedge, a axe head, a inclined plane, a ramp, a lever, seesaw, wheel, and axle, biking,
Yep.
old egg beater,
There you go. Those are, yep,
pulley, and sail on a boat.
Perfect. All right, good. Those are good. As long as you have something like that, you're good to go. Lastly, what kind of lever is the pop top on a soda can? Who's got that one? Eleanor, what do you have?
Second class lever, the fulcrum is at one end and the input force is upward at the other end.
Sometimes, so it depends on what the type of pop top is, but the type you're envisioning, yes, is a second class. There's another kind that you pull differently, and those can be first class if you were envisioning that other kind. So,
Like the ones that in like a soda can, like
yeah.
clicking.
Yep.
Is that the first class? 'Cause
So
that's what
if
I
you're,
did.
so technically those are second because, I mean, those are first, sorry, because the fulcrum is actually that little
Okay,
piece
I
where
was
you
right.
pop it off.
Okay, I was
Yes. So if
because
you're,
when she said second class, I'm like,
yeah, the kind that looks like a Coke can, those are first because the actual fulcrum is that little metal dot where you can pop the thing off. Any questions before we move on?
Do you like post these on the?
No, I mean, I just give you, if you didn't do them, I take credit off, but if you did them all, even if you didn't get them right, that's fine. Because the point of homework is to practice. All right, I'm gonna leave these out during lab, and if you get done and you want time to come and fiddle, you're welcome to do that. So what you need to do now is get yourself over with your, do you play it?